So we're going to look at justifying or proving theorem 1 for the Taylor series. So where we can get the coefficients of the terms by using the nth derivative at the center C divided by n factorial. So this coefficient, this is what we use for Taylor-Maclaurin series. Maclaurin series is just a special case where the C value is equal to 0. So it's a simple case, the simplest case of the Taylor series, but we'll just generalize it for any center C. Okay, so I've drawn here f of x, this just random function, f of x, and we want to build this Taylor series polynomial for this. Okay, and so what we can do, what we have to have is, first of all, a couple conditions to be able to do this. We need to know where the center is. We need a starting point to do this. Okay, so we need to know where the center is, so we need to know that coordinate right there. And it must be differentiable at that center. We must be able to find derivatives at that center to be able to do this. Okay, so what we can do is we can just start building this Taylor series polynomial that we call p of x. We're going to build this polynomial series. So we'll just start with the very first term of that series, and it's just going to be a constant term, a0, okay, or a0. And we need to know where a0 is, and in fact a0 is just that. This is the original point. Okay, so it's just going to be f of c. And so basically we have this approximation, this polynomial here. That polynomial is just going to be this constant line, and that's going to be p of x. Okay, and obviously that's, as an approximation for the green function, is not great. Okay, but there it is, and we can just verify that it actually works. We can just plug in C, the center, and see that it works. And yet we plug in C, we get f of C, which is, so a0, which is the same as f of C. Okay, so there it is. There's a0. Maybe I'll write that into my picture here. So f of C is equivalent to a0. Okay, so if we look at that, that's f of c and a0 are the same coordinate. Okay, so there it is. There's my polynomial. Not great, but certainly does work. Okay, so this is this p of x equals c, basically f of c. This function is our Taylor polynomial for the first term, and it's really kind of a crappy, it's not a very good approximation. Okay, but we'll just write that down. When n equals 0, we have a0 or f of c. Okay, so let me just write, I'll just do that in a different color here. We'll just keep track of all this. So there's our first coefficient, is going to be f of c. Okay, so we want a better approximation, so we're just going to get rid of that. And we're going to add one more term to this Taylor, this polynomial series. And so we're just going to start with our f of c, and we're going to add the next term, a1 times f of x minus c, where c is the center. And we don't really know what a1 is. Okay, so we're going to figure out what a1 is. So when we do this, essentially what we've done is we've built a linear function that approximates that curve. Okay, so our linear function that approximates that curve looks like this. And this is really just a linear approximation function, and we use a linear approximation, we find the slope at c, and then use the linear approximation formula. So that's all we're doing. This two-term polynomial series just ends up being the linear approximation function that we've used before. So when I plug it into my formula, right, I get the derivative at c, the derivative at the center, or the slope at that point, times x minus c plus, our y coordinate there. Okay, so this is just my linear approximation formula. Okay, and that's my second term of my polynomial series. And basically, we could do some other algebra, which we will later on, but we can make a simpler relationship. We can just say, well, this is my linear approximation formula. My linear approximation formula looks exactly like this. So I know that a1 and f prime c must be the same. Okay, we can check it. Right? We can check it by plugging in p of c. Yeah, it's going to be the f of c value, and then when we plug in the c equals c, or x equals c, we get 0. So this just, yeah, this is perfectly good. This formula is perfectly good, and it works at c. Okay, so then we all, but really by this relationship here, right, this two-term polynomial is the same as a linear approximation. We can just make that kind of connection here. So I'm going to write that in now. So when n equals 1, we're using f prime at c. Okay, so there it is. There's my f prime at c. So I'm going to continue going on here. I'm going to add one more term to this. Okay, so I'm going to add one more term to this polynomial. So now I get f of c plus f prime of c times x minus c. And then I'm going to add my next term. This is a2. And this is it basically becomes a quadratic approximation formula. Okay, so now instead of using this linear function, I'm going to now use a quadratic function to approximate that graph. Okay, maybe I'll just do it in purple here. And we've seen before that as we increase the number of terms, okay, as I increase the number of terms, you know, this becomes a better and better fit. So there's my quadratic approximation formula. Okay, and so I want to be able to find the a2 of this quadratic approximation formula. Well, I can do this by checking, I can find a2 by checking the derivatives. So what I'm going to do first is I'm going to differentiate the p function once. So I get, you know, fc, that becomes 0. Okay, so that disappears. This is a linear function, so the slope of the linear function becomes the derivative. And then to do the derivative of this, I need to apply power rule, so I get 2a2, and now I'm down to linear function. Okay, and I can test this. I can actually test this. I can say, well, let, you know, x, if at x equals c, do I get the right derivative? Okay, at x equals c, I get f prime of c is equal to p prime at c. Yeah, that's true. Okay, so this is good for that derivative. So I'm going to differentiate one more time. And to do that, when I do that, I'm going to get rid of this constant now. Okay, remember that's a constant value because it's evaluated at c. And then since this is a linear function, it differentiates to a constant term. And I'm going to make the assumption, and not really an assumption, but this is because I tested f prime with it worked, f double prime should also work. Okay, and I can then say that, well, the second derivative of f is going to give me the coefficient 2a2. Well, I can then solve for the second derivative by just rearranging this into, well, 2a2 is equal to the second derivative evaluated at c, okay, because we know that we can do the derivatives at the center, and then divide by 2. Okay, so we end up with this expression, and I'm going to just make a little bit of leap here and say that's not 2, that's 2 factorial. And we can kind of see why, because as we differentiate, okay, if we differentiated the first time, imagine the a2 here, there's that power of 2 goes onto it once, okay, goes onto it twice, and then you differentiate one more time, you have, you know, you can times by 1 as well, so it becomes 1 times 2 times 3. Okay, and we can go to the next one. It becomes 1 times 2 times 3 times 4 because we have to successively differentiate the powers. So as we successfully differentiate, those powers end up going front and goes down, right? Imagine if it starts at, you know, x to the power 5, it's going to go 5x4, then it becomes 4 times 5x3, and it becomes 3 times 4 times 5x2, and then we get this factorial going on that coefficient. So that's where I get that n factorial. Okay, so now we can kind of see that this is where it's leading to, and we can, by induction, if we do this one more time, we can induce that by induction, say that, well, we can just generalize f, and this should say n, okay, f to the nth the nth derivative, okay, evaluated at c divided by n factorial is going to give our an term. Now, you can stop the video here if you're convinced of that, but if you want, we can do it one more time. If you're not sure about that n factorial, we can see exactly where that n factorial comes from. That n factorial then, if we just do one more term, this is my cubic approximation formula. So if I were to kind of go back to my derivative here, my function here, now I'm dealing with this, function. It's going to match a little bit better now, even a little bit better. Okay, so there's my cubic approximation formula. And I can then say, okay, well, if I can check these coefficients by differentiating again. So I can differentiate once, okay, I get this. I can differentiate twice, I get this. And now you can you see how that 2 times 3 is showing up? Okay, and then we can check this derivative at 0. So we can say p prime, the second derivative at 0. Okay, so I'm just going to write down here. P double prime at 0 should be equal to f double prime at, sorry, not at 0, but at c, at the center, should equal the second derivative at the center. And as we differentiate this, a2 here is my 2a2 is my second derivative. Okay, so, and I don't know why I didn't follow that along, but that term is that term there, which is that term. So when I plug in c, I get 0 minus c minus c, which is 0. So I am with my second derivative confirmed. Okay, so I can confirm my second derivative, and then I can do by induction. I can say, well, I can differentiate one more time, and then say the third derivative also is equivalent at that point, and we can solve for then the coefficient a3 by dividing that third derivative evaluated at c by the coefficients 2 times 3, or again, you can see that it starts becoming the factorial notation. So there it is. But there is our theorem 1, how we get the coefficients of the Taylor polynomial series.